Welcome to the 8th and final episode in Radio Design 401. Today we're going to talk about low noise amplifier design, but also how the low noise amplifier fits into the entire receiver. And we're going to concentrate on system testing today. We're going to take our radio, which you see down here, out into the field in a number of environments and test it to see how well it does and how well it compares to things like radios in automobiles, which are some of the best FM receivers out there. Now, I chose this title very carefully, as I always try to do. I want to capture what we're going to talk about, but I also want to make it appealing, right? And today's episode is called LNA Design and System Testing. I think that captures things pretty well, but let's see. I typed this into Google to see what else is out there on the web dealing with this topic or these topics. And here is Google's AI response. LNA design involves systematic process of selecting components and topologies, i.e. the circuit designs, to amplify very weak signals while adding minimal noise. Okay, that's good. But then it went on to say, to achieve specific performance goals, gain, noise, etc. Now, I can't help myself, having graded many papers over a couple of decades, I always edit stuff. So I edited this, as you can see. I wanted to say, amplify very weak signals while adding minimal noise and achieving specific goals like gain, noise figure, stability, linearity, which we've talked a lot about recently, etc. System testing then verifies that the fabricated LNA, so we're going to talk about the LNA that we built, meets these specifications and functions correctly within the overall receiver. So let's see how it fits into the overall receiver. Here is the latest rev of the block diagram for our Radio Design 401. And if you've seen the most recent episode before this one, i.e. episode 7, then we went over that there. So I'm not going to go into it in great detail here, but let's just take a single pass through it. On the left is the LNA that we're going to be talking about today. We'll also talk about some basic LNA design techniques. But this one is a so-called Q-enhanced LNA. And within the receiver, it makes us have a tracking pre-select filter design. And because of the enhancement that we're going to review, we start out with, say, a 3 megahertz bandwidth, which we can tune across the band as we tune in different stations, but we narrow it up with feedback to 200 kilohertz. Why 200 kilohertz? Well, that's the bandwidth of the single channel. So after we've done that and amplified it sufficiently, we move on to our mixer with a local oscillator and the IF filters, and eventually the DMOD over here. And a simplified view of that overall block diagram is shown here with the Q-enhanced LNA circled. What it does is it creates a frequency response, as you can see, that is very sharp, i.e. the channel width, and it provides image filtering, but mainly pre-select filtering to protect the low noise amplifier from the very strong signals that are out there. Where are those strong signals? Well, let's go back to our cover slide. Well, here's one case where we're going to go up to what's called top of the world. And there's a antenna tower here that has an FM station at 96.3 FM. And it's blasting out about 20 kilowatts of power. And we're parked here, and we're going to show how our radio can tolerate that and receive very weak stations even in the presence of that strong one. But we're not just testing it against ridiculously strong signal environments. We're also going to test it in other environments. Here we are in a park, which is near my house and a couple of miles away from that tower. But the land topology between the tower and here is such that that station is not that strong here. So this is a more benign environment. What you see is our new radio sitting on the console here. This is the Q-enhanced LNA, and this is the rest of the radio. And we're going to try to tune in 94.1 FM, which is a pretty darn weak station in the midst of all those dozens of other signals that are out there. I've got an antenna on the top of the car, and it's roughly a half-wave dipole. And the car itself, as we've discussed previously, also has effectively a half-wave dipole. And we're going to see how our radio compares to the reception ability of the car, which, by the way, operates at about 10 times higher current consumption than ours. So, before we get into all the main topics we're going to talk about today, let's take a listen to how our radio worked in that really strong signal environment. Okay, success. We are at the top of the world. There's that big antenna over there at 96.3 pumping a huge signal at us. And we've got our Q enhanced filter here. I set up a little bit of attenuation on the front end, not too much, and dialed in some Q enhancement. And we're picking up 88.1. But it's coming from here, our radio, out of these speakers. Let me turn up the car radio so you can hear what it does up here. So that's absolutely terrible. But that's our radio, and it's working great up here. All right, how did we receive such good performance relative to very expensive? The radio in this car costs $1,000, $2,000 to replace. Our bill of materials is probably well under $100. So how did we do that? Well, that's been the subject of Radio Design 401 all along. But here's what we're going to talk about today. We're going to look at different signal environments. For example, noise in indoor environments. Also, even in that park, there are still dozens of signals which can mix together through intermodulation that we discussed in episode 4 of this series. We didn't emphasize there, though, that the IF filter is also very important. So in Radio Design 401, we have used a much better IF filter configuration. And then lastly, testing at the top of the world. I didn't come up with that name. It's actually the name of the street that this thing is on. Cool, huh? Okay, so after we say a little bit more about those signal environments, we're going to just show a little bit of background in prior episodes in case you're a new viewer for this channel and you haven't seen some of those. In particular, we have Radio Design 101. It's a different series or class on this channel, and it's modeled after a university class. All right, so after that background and brief review of prior episodes, we will get into LNA design and talk specifically about our design, but also about just how low noise amplifiers are designed in general. And then classic lab testing, where we look at the gain, the noise figure, the 1 dB compression point, and the power consumption. But then we really want to get to the real world test that I just showed you and see how the radio compares. And then we'll finish off with some conclusions and future directions. Okay, back to signal environments. This material is covered in some depth in episode 3. However, I wanted to emphasize a couple of points here. This is my home laboratory, and you can see the spectrum analyzer here. It's hooked up to this dipole antenna, and this telescoping segments are adjusted so that it's basically half-wave dipole at the FM band. Now let's focus in on what we see on the spectrum analyzer that's shown here. To orient you, we're going from 85 megahertz to 110 megahertz on the frequency axis. The vertical amplitude axis is scaled as we normally do to 10 dB per division, and the reference level, the top line up here, is minus 20 dBm. That's a fairly strong signal. Our goal is to receive very weak signals, even in the presence of strong signals. So where are the weak signals? Well, they're down here, or they're supposed to be down here. A perfect receiver with a really good low noise amplifier with a noise figure of 3 to 5 dB should be able to see signals down to this bottom line. But you can't. And is that due to this tiny SA spectrum analyzer limitation, or, well, no, it's not. It's due to radio frequency interference in the environment. And you can see that most prominently over here on the left side at the low end. This is basically noise. So any signals that are down to 110 or minus 120 dBm are covered up by that noise, and we're not going to get them. So that's a problem in these indoor environments. And where's that stuff coming from? Well, all of this equipment is off, but there's lights in the room, LED bulbs, and there's a computer behind this desk. So it comes from everything in your house basically these days due to switch mode power supplies. So indoor environment, maybe not the best place to test. So I loaded up our radio and of course this spectrum analyzer into my car, and I drove over to the park nearby. And with the antenna on the roof, as you can see here, and routed into the car with spectrum analyzer, let's see what we get. The noise floor is now minus 110 dBm, which is not perfect, but over here on the right-hand side, it's closer to what we would expect to get, which is minus 120. So where is this noise coming from and all of this, and why are these areas so elevated? Well, it's probably due largely to intermods, which is what we discussed in great detail in episode 4. So if you're interested in that, have a look at episode 4 sometime. But I think we're also being limited in this particular spectrum analyzer trace by the IF filter being used. So I had this spectrum analyzer set to a resolution bandwidth of 100 kilohertz. And in the FM broadcast band, the stations are spaced by as close as 200 kilohertz. So the filter can't roll off enough to be able to see stations adjacent or between if they're very, very weak. And I think that's what's going on here. All right, let's move on. Here we are back at top of the world. Oh, by the way, the low noise amplifier in the tiny SA spectrum analyzer was on in this shot. That's why we should be able to receive signals down to about minus 120 dBm, based on stuff we discussed in episode 2, where we talked about signal to noise ratio, noise figure, and receiver sensitivity. Here, I had to turn the LNA off because if it's on, the strong signals up here at top of the world just blow away the front end, the low noise amplifier of this tiny SA. So the LNA is turned off in this shot. Also, I set it at 30 kilohertz for the reason I just discussed. So now you can see that we can get some pretty weak stations, but not down to minus 110 or minus 120. This is minus 90 here. The bottom is minus 100. So that's really due to the limited dynamic range of this receiver. Spectrum analyzer are receivers, right? So spectrum analyzer has the same kind of issues that we've been trying to address in our receiver designs. But we can see some spaces between the channels that we couldn't before because we got the resolution bandwidth set to 30 kilohertz. Yay! So here, up at top of the world, the noise floor, the minus 100 that we're seeing here, is really dynamic range limited. And that's partly due to the fact that spectrum analyzers are designed to see all kinds of signals. They don't have pre-select filters for tuning and so forth. I also think that some limitations are due to spurious emissions. So this tower is putting out, let's see, the actual transmit power is 7.5 kilowatts. The effective isotropic radiated power is 21 kilowatts. That's a lot. Of course, by the time it gets over to this antenna, it's spread out everywhere and it's not pumping kilowatts into this antenna. But it is pumping minus 3 dBm, or probably 0, which is around 1 milliwatt. The reference level up here is 0 dBm. And radio transmitters are not perfect. They have their own limitations. And one is that if they're pumping out signal at a particular frequency, there is some what's called spurious emission at offsets from that frequency. My guess is this tower completely satisfies FCC rules, but those rules aren't going to specify that you have to have absolutely no emissions at say 200 or 400 kilohertz offset. So it looks good here, but in this region down at the bottom, it looks like I think those are spurious emissions. All right, our next topic in our presentation outline is background and prior episodes. So as I previously mentioned, there is another course or series on this channel called Radio Design 101, which focuses on circuit level material, such as you see here on the blackboard. This is material that I taught for like 20 years at the university. But it wasn't just a circuit design class. We were actually designing and building radio receivers, like the one you see here. And part of Radio Design 401 came from looking at the performance of these radios that we built over the years. We've built, literally designed and built hundreds of subtly different radios because each student has to do their own design. And the performance was good, as I'll show you, but not perfect. And so Radio Design 401 is a deeper dive into how to design radios. But if you want some of that background material before going into Radio Design 401, then you can get it from the 101 series or you can go out to our website. And there's lots more stuff on the website, including antennas and circuits in general and Fourier transforms and everything else. So hope you enjoy that. Now, how well did the receivers that were designed and built in the university class work? Well, they work pretty good, but let's take a look. Here's the final exam. It's not an in-class exam where you sit down and you solve problems. The final exam in this class was graded by physics. How well did you make your radio? And what we did is we checked it off. Now, I did talk to the students and try to probe and see how much they understood all of the nuances of circuit design, but largely it was looking at the performance of their radio. And if we had done our designs well throughout the semester, we should be able to meet these specifications. The first student to check off got DC power of 52 milliamps, that's with the volume all the way down, and they had a tuning range which was a little bit better than what was needed, which is perfect, that's what you want. And the sensitivity was minus 114 dBm, that's with a lot of noise, but by minus 90 it was very, very clear. So this is pretty close to ideal, this is excellent. And the audio frequency response, it says 2.2 kilohertz, that has something to do with what's called de-emphasis in FM broadcast receivers, and that's exactly what it was supposed to be. Let's go over to the right-hand side. So we were able to receive 17 stations with great sound on this radio. And the next one got 21 stations. It also had great sound, and I swear I can't read my writing, but I'm pretty sure this says SYNTH. This is a notation to myself that they had the frequency synthesizer implemented, which was optional. They didn't have to do that. This one got 20 stations, very clear, and so forth and so on. So receiving 20 stations is about right. This spectrum analyzer trace was taken some 8 years later, and there are actually more stations in our area now. So I count about 26 here. So every one of these vertical lines is, of course, a station. So at the end of our Radio Design 101 series, where we covered the same kind of material that we covered in the class, but in less detail, I posted some epilogue videos. And in those videos, I was looking at the number of stations I could get with the radio that we designed in Radio Design 101. And here's that radio on the circuit board. And you can see that I'm just using a little whip antenna, and under that is a little score sheet. And what I did is I compared that radio's performance to the performance of a couple of commercial ones, like this big one back here and this smaller, newer one here. And here's how well we did. At the end of the Radio Design 101, after the final episode, but before the epilogues, we got this many stations. So we're pretty happy. I mean, the radio is receiving and sounds good, but we weren't getting the weakest stations out there. So in the epilogues, we did some improvement on the radio, and we got more stations. We also tested those commercial radios. The small one it didn't do so well. In fact, we did probably arguably better than it did, unless we turned the attenuator on in it. But that big old radio with the colorful dial got a whole lot more stations than any of us. And why is that? This colorful big radio was designed and built in the 1970s, whereas this smaller one is probably from about 1990s or so. So it has nothing to do with how old the radio is. In fact, the old radio, as it says here, old radio, is better than the newer radios. And part of the reason is captured in this block diagram. The old radio has this knob here that tunes some capacitors inside, and you can see one of them right here. This is its low noise amplifier. It's just a simple common base design like we've been talking about in our prior episodes. And the amplifier accentuates signals in about a 4 megahertz band at frequencies which are determined by this variable capacitor in the tuning, and it tracks the local oscillator. So over here at the mixer doesn't get hammered by too many signals. So it improves the performance of this old radio relative to the newer ones. Sadly, this one is not perfect. They just did a fixed 2-pole broad filter on the front end. And that was a mistake, and one that we're going to be correcting. To correct that, we need a pre-select filter that tracks with the local oscillator tuning as well as the image filter does. Now, our Radio Design 401 low noise amplifier is not the only thing that we changed from those other designs to get better performance. Another thing that we've done is to improve the intercept point performance of the mixer. And we use a couple of IF filters in Cascade to get a sharper and more thorough roll-off of frequencies outside the single channel that we want. And finally, we have more IF gain that will get us the sensitivity we want. So there's a lot of subtle things that went into this new receiver. And if you want to review all those subtle things, remember, this is episode 8, the final episode in this series. There were 7 before that, and some of them were broken down into multiple parts. So we started in episode 1, where we discussed low power receivers. That's our goal, so that we can operate for long times on batteries and make them perform in crowded spectrum environments like you've seen. And Radio Design 401, relative to Radio Design 101, is an advanced course. In it, we've talked about all the things that make receivers work well. For example, episode 2 dealt with signal-to-noise ratios, noise figure, very important for low-noise amplifiers, right? But it's not the only thing that's important. There are other things that affect how weak a signal you can get. So it's one thing to have really good noise figure and great sensitivity in the lab, but you get into environments that are real, like noise in buildings, and the noise figure doesn't really matter too much anymore. Sad, but true. Now, if you're doing satellite receivers, then yeah, you got to have a low noise figure. But for a lot of terrestrial applications, we showed in episode 3 that radio frequency interference is really a limiting factor. And perhaps the biggest limiting factor is the thing we covered in episode 4, which is intermodulation distortion. And that's why we need filtering. In episode 5, we started our semester project, and we went through this block diagram in great detail. So I definitely refer you to episode 5 for some more detail on the design of the block diagram. And then we took a step back in episode 6 to look at LNAs and noise analysis. Because if you're not doing terrestrial things, then you do need a very low noise figure. So you need to understand circuit design and noise and how to minimize the noise added by the low noise amplifier. And that brought us to episode 7, the one right before this one, where we covered the architecture of the whole radio, except for the Q enhanced filter. So this one just had a tracking image filter that I tuned manually. Okay, so that's a lot on system requirements, but that is really, really important. It's one thing to design a low noise amplifier and have a great noise figure and you can market it and people will buy it, and that's great, I guess. But if your goal is to create a really excellent working receiver, you need to be looking at the system at the same time you're doing the low noise amplifier design. And that's what the AI was trying to say here. System testing verifies that the fabricated LNA meets these specifications and functions correctly within the overall receiver system. But it's actually deeper than that. You really need to be focused on the system and then design your LNA accordingly. Which brings us to LNA design, the main focus, or one of the main focuses of this episode. So what's the difference between an amplifier, an RF amplifier design, and a low noise amplifier? Well, not very much, really. Let's take a look here. This is from Radio Design 101, so hopefully this is a review for a lot of you. There are 3 or 4 basic topologies that we deal with. There's the common emitter amplifier that most of us probably know, where the signal comes in on the base, the emitter is AC grounded with this bypass capacitor, and the output comes out here on the collector. Now, in an RF amplifier, there's more to it than that. We usually have matching networks, impedance matching networks, to get as much of the signal as you can from the antenna, so maybe that's where this is connected, into that amplifier. And there are also some capacitances in the transistor devices, and we can do what we call absorb those into the matching network design. I'll let you look at Radio Design 101 for more details on that. But we're trying to get as much of the signal in as we can so that any noise generated in this transistor is minimized compared to the amplified signal. Now, in the basic types of amplifier configurations, or as the AI would call it, topologies, there is also the common base that we've talked about extensively in both Radio Design 101 and 401. In the common base design, the base is AC grounded with a bypass capacitor here, and the signal comes in on the emitter and goes out on the collector. Let's see where that's used over on the right-hand side here. So the output of Q1, this common emitter stage, goes into the input, the emitter, of Q2, which is a common base stage by virtue of this bypass capacitor. At the output of that is an LC tuned circuit, and this is where the filtering takes place. And then if we need to, we match down to, say, whatever the input impedance of the next circuit is. And this configuration is called a cascode amplifier. And we didn't really cover it in Radio Design 101, except when we got to the end in the epilogues and in the appendices. So it is covered there if you want to delve into it. Now, to get really deep and sophisticated, let's take a look at this UHF fully integrated LNA. This shows some of the sophistication that may be included in some low noise amplifiers. First of all, the input impedance of a cascode amplifier is usually quite high. So this matching network is generally going to match up from, say, your antenna at 50 ohms to something like a K ohm. And in the process, you get a voltage gain, and that really helps lower the overall noise. Because remember, the more signal you get into this thing, the better it does competing with noise generated in the transistor. So that's done right here with this so-called L match. So the voltage here is higher than it is at the input because we're converting to a higher impedance. Now, it gets tricky. Number one, these are MOSFETs, but I've drawn them in such a way that hopefully they remind us of BJTs. And they really work pretty much to a first order like BJTs, so don't worry about the MOSFETness of them. The other thing is these are P channels, so they're like PNP transistors instead of NPN. So this configuration is flipped vertically relative to this one. But the signal is coming in on the gate here, which is like the base here. And then there is the cascode transistor. And then here is that tuned circuit, which in the top diagram is up here. What is L2 doing? Well, it's doing two things. In the literature, if you look at this, you will find that people put L2 in to make the input impedance of this device more resistive and lower. What they don't often talk about, but is perhaps more important, is that this inductor here will help get you a much better noise figure, because noise currents in this transistor will come into L2 and see a high impedance, and they'll generate a voltage which then comes back into here, and it cancels the current that started all of that. It's very confusing, but it works. So in a nutshell, L2 is a trick to get a better noise figure. The rest of this is a so-called balun or unbal, where we take a single-ended signal and translate it to a differential signal. Because we're doing this all on an integrated circuit chip, and when you do things on ICs in analog, you often like differential signals. So you don't have to have bypass capacitors as much. So then it is buffered at the output by these guys, where you come in on the gate and come out on the source, which is what you're doing over here, except you're coming in on the base and going out on the emitter. But again, transistors pretty much the same. This should look more familiar. This is the low noise amplifier that we were talking about in episode 6 of Radio Design 401. So just a couple of episodes ago. It is a common base design where the input impedance is usually small. So we actually converted down from a higher impedance to a lower impedance. And then it gets amplified and comes out here. Here's the tuned circuit. And then it is converted to another impedance. And in our radio, the load resistance over here is what we see looking into the mixer stage. And so it's about 50 ohms. So we do have to convert down, and we will be doing that. Over here on the right-hand side is also from episode 6, where we analyzed the noise figure and then we ran simulations to figure it out and make sure we had what we wanted. And to make a long story short and not repeat everything in episode 6, we got 4.5 dB, which, okay, it doesn't sound great. It's not a 1 dB noise figure, but again, remember, the noise figure for terrestrial designs doesn't usually matter very much in the system context. And that's because in an indoor environment, the radio frequency interference often increases your noise floor by 20, 30 dB or more. We've seen situations where it increases the noise floor by as much as 70 dB in a commercial building. It's insane. But even outdoors, things like intermodulation distortion can make the noise figure that you have not that critical. So here's a good example of that. This is from a combination of episodes 4 and 6. In 4, we explained intermodulation distortion. Basically, if you have a couple of strong signals or several strong signals, they can mix together and produce new signals that aren't actually there in the real environment. And that's what we see here on the spectrum analyzer. The sweep is going from 85 megahertz up to 115 megahertz. There should be no signal right here. This is actually caused by mixing of some of these stronger signals. Likewise, at the top end, up to 115 megahertz, yeah, there might be some aircraft signals, but these are not them. And in episode 4, we discussed how you can figure out if these are real or not. Basically, you turn on an attenuator, and if they drop a lot, then they are intermods. And the reason we're getting all these intermods is because the low noise amplifier in the Tiny SA is on. And here are the specs up here. It has a 1 dB gain compression of plus 5 dBm and an associated gain of about 25 dB. So the 1 dB compression point at the input of the amplifier is about minus 20 dBm. So we're getting very close to that here. In fact, when I was doing these measurements, this one was compressed a little bit. And intermods happen long before compression does, so that's why you've got such a mess here. Also, in those prior episodes, we looked at this example, which is a GPS antenna for marine. And the thing you can do to combat intermods and not give up on having a low noise amplifier is to filter out all the strong interferers before they hit your low noise amplifier. That is fundamental. That is what we're talking about in this video. if you want to design really good receivers, you need filtering at the front end. And here, this is the antenna, and there's a little pin right here that goes through to the backside, and this is the backside of this plate, and this is that pin. So the antenna signal comes in here, and the first thing it hits is a filter. And that's before you get to the low noise amplifier, which is here. So what is the upshot of all of this? Well, it is filtering. We really need good pre-select filtering before our low noise amplifier, unless we're in a benign environment like a satellite dish pointing up into the sky and there's no strong signals anywhere near. But for everything else, we need a pre-select filter before the LNA. And this is what I'm calling an ideal low power receiver. If we can make that pre-select filter very narrow, i.e. the bandwidth of the signal that we're interested in only, and not let anything else through, then there's no other signals to hit the LNA and cause intermods. So the LNA doesn't have to run at very high powers to combat intermods, another thing we talked about in prior episodes. So it is this pre-select filtering that we need. And in reality, we probably want a variable attenuator in front of it as well. So this stuff is discussed in this document, which is my dissertation that I wrote a long time ago. And we did some Q-enhanced LNAs in that work. But this is from the radio design series material. What we're trying to do here is get something that basically looks like this, where we have narrow image filters and a pre-select filter, and they both track and tune when you change the frequency of your receiver. And with the Q-enhanced LNA that we're focused on, we do that by having the LNA, having the output tune circuit, and then feeding some of that signal back to the input. And what that does is it amplifies the signals at the input more than they would be otherwise. It used to be called regenerative receiver design. But we now have microprocessors and more sophisticated electronics, and we're able to get over the problems that prevented those receivers from going forward back in the 1920s or 1930s. We can now revisit that and make these things work. We just have the amplifier, we have a filter, and then we feed back some of the signal, and it effectively creates filtering at the input, as we will show. Here is one implementation of that. Q3 is our common base amplifier. This is our tune circuit. Then we're buffered by Q4, and that signal is fed back. And through the magic of Kirchhoff's current law, it basically adds to the signal that's coming in. So you've got a current going this way, you've got an input signal current going this way, and those two combine and come in here. So we're adding the feedback to the input signal. As we would expect, the tune circuit creates a bandpass response. But the neat thing is, if we adjust the amount of feedback, we can get that bandpass shape to be very narrow. So it's going to block all the other channels. Yeah, maybe the adjacent channels are not attenuated too much, but they are attenuated, and other channels are really very weak. But more importantly, let's see what happens at the input. At the input, we also have a bandpass response. So this is pretty cool. Now it's biased at 1.2 milliamps, so we were really going for low power at this point, consuming 6 milliwatts compared to like a car radio that might consume 100 milliamps, so several hundred milliwatts. In our latest implementation, we've backed off on that. So we're not trying for super low power, we're just trying for like an order of magnitude less than in the car radio. So this one runs at 11 milliamps. And this is our latest Q-enhanced LNA. This is the one that all of the testing I'll show you was done on. And it beats the automobile/car radio performance at 10 times lower power. The architecture is pretty similar. There is a attenuator here if you want to dial some in, or you can set it to 0 and not have any attenuation. The signal comes in. It is Kirchhoff's current law added to the feedback, which is from this emitter-follower transistor, and those go into the common base design. So basically the same thing. But this transistor is biased at about 5 milliamps, and this transistor is biased at about 5 milliamps, so we can tolerate somewhat larger signals. The other thing that's different here, previously we had a gain of 30 dB to the final output, but that's too much. That's going to overpower the mixer. So we backed off on that by using a really cool RF design trick, and that's best seen over here on the lower left. The output signal comes out of the collector, and oh look, there's not an L in parallel with a C. There's an L in series with an L, and then that's in parallel with a C, and there's a resistor here. This is just to model the quality factor losses in the inductor and the capacitor. So assume this is 0 ohms. For simulation, I put it in so I'd get a pretty accurate simulation of what the real world will do. All right, but what is going on here with this tuned circuit? It's kind of weird. Well, it's not weird if you just look at L1 in series with L2 and have R3 be 0 ohms. So L1 in series with L2 is in parallel with this capacitor. So it's just a simple LC network. But it is tapped. And way back in Radio Design 101, we did cover this in the impedance matching episode. What's going on here is at this node, down here at the bottom, if we look at the impedance from this node to ground, where's ground? Well, ground is AC ground is up here. So from this node to up here, and if we don't have anything connected here or here, then based on the values and the frequency, we'd have about 6 k ohms from here to ground. But if we look at this as a matching network, as we did in Radio Design 101, and we say what's the impedance from this node to AC ground, it would be about 250 ohms. So why? What are we doing? Well, remember the gain of this device is GM times R, where R is whatever you see looking out the collector. So 250 ohms here. There is some loading, but I made the loading light, so just think about it being 250 ohms. The gain from the input to this point right here is much less than it would be than if this was tapped in up here at 6 k ohms. So GM times 250 is much less than GM times 6,000. And that's the point of all of this, is to back off on the gain. So here's what our final design looks like in reality. The tapped inductor, L1 and L3, C1 is just a coupling capacitor, so ignore it at AC. It's just a connection from here to here at AC. And then the tuning capacitor is a combination of these two integrated circuits and a fixed capacitor over here, C6. So these ICs that implement digitally tuned capacitors are from PSIMI, and here are the part numbers if you want to look them up. They are also covered in episode 1, part 3 at about the 30-minute mark, I believe. So the level of Q enhancement is adjusted with this variable resistor over here, which I'll show you in the circuit board in a second. And there's a RF gain control or attenuator, depending on how you want to talk about it. And it's just a variable resistor from 0 to 500 ohms. Over here on the left, we can see the actual implementation. The inductors are fairly large. Do not try to do this with surface mount inductors, because the quality factor of these inductors is very important to get both the gain and the noise figure, both of which are very strong functions of the quality factor of the tuned circuit. So these inductors have Qs of about 120, and we're going to enhance that up to a Q of about 500 by adjusting this little potentiometer right here. And this is the RF gain control / attenuator pot. The tuning of the frequency comes in on these digital control lines because it goes to the digitally tuned capacitors. All right, let's see how we do with this circuit. Let's see how it performs. Here's my lab setup for most of the measurements we're going to see. There's a signal generator over here, which is basically a tiny spectrum analyzer that is switched into signal generator mode. And its signal comes out on this coax. It goes into this step attenuator, and then that goes over to the input of the Q enhanced LNA. whose output is then fed to the spectrum analyzer, which is a tiny SA Ultra. So yeah, this is kind of messy. Sorry about all the background clutter, but hey, I wanted it to look like a real environment, and this is the way I actually do it. You may notice that I'm not using a nano VNA here because mainly I'm interested in gain and noise figure, and I can get that using the signal insertion gain measurement method, which we've talked about in previous videos. And all we need for that is a good calibrated-ish signal generator. In fact, it doesn't even have to be that calibrated because we're going to do insertion gain. So see those previous episodes if you want to understand that more. And we need a good step attenuator and a decent spectrum analyzer. And that's what we got. And here's the results. Lab test results. This is with the filter bandwidth adjusted with the Q enhancement pot to about 200 kilohertz. The DC power is 11 milliamps, spot on with what the design and simulation were. The gain is 18 to 22 dB. It depends on which end of the band I'm at and precisely what the bandwidth is, but we'll just call it 20 dB. It checked off as 22 at 109 megahertz. Why 109 megahertz? Well, because inside the FM broadcast band, even without an antenna attached, the inductors would tend to pick up some signal and I couldn't see the low-level stuff. So when I was doing the noise figure, I wanted to be able to see it. So I just did the gain check at that frequency too. The noise figure ended up at approximately 5 dB, which is pretty much what was expected. And then the really important stuff is down here. This is the 1 dB compression point information at the input. So it's input referred 1 dB compression point. And on channel, when the gain was high, it's minus 30 dBm. It's not great, but that's okay because we got an attenuator out front. So if we happen to be tuned to a really strong signal, we can turn an attenuation in and it's all fine. What really matters is at 2 megahertz and above, or at some offset frequency. And there, it came out to be minus 10 dBm. That's a really strong signal. And I'll show you how we measured these things. First, the gain. Here's the signal generator. I had it set to 109 megahertz, and the level is set at minus 30 dBm. But I don't take that at face value. I connected this directly to the spectrum analyzer, and it in fact read minus 30.0 or minus 30.1 or something, so close enough. Then that signal goes through this step attenuator, and during the testing of the gain, I am clicking in 2 20 dB steps, so a total of 40 dB attenuation. So how much signal do we have coming out and going into the input of our filter? Well, it's minus 30, minus 40, right? So we got minus 70 dBm coming in here. These could be off a little bit, so I haven't accounted for that. So I'll just say at the end plus or minus a dB or so, whatever. So we have minus 70 dBm coming in to our device under test, our LNA, and it has been previously adjusted to have the right bandwidth of 200 kilohertz. And the output is shown over here on the spectrum analyzer. It's minus 47.9 dBm. Now remember, this spectrum analyzer is the same one used when I measured this minus 30 dBm coming out of this. So I'm essentially getting an insertion dB gain. It will be dependent in accuracy on how good this attenuator is, but I think this thing's good to about a dB or so. The calculation is shown down here. The gain is the output minus the input. And that works out to be 22.1 dB with the filter bandwidth adjusted to 200 kilohertz. Okay, so now let's measure noise figure. And remember, I'm not interested in something that's only 1 or 2 dB noise figure. We expect this thing to be about 5 dB. And so an accuracy of plus or minus 1 dB, that's fine. So I don't need a calibrated noise source. I can do this the old-fashioned way. And what I did is I set the spectrum analyzer up to a center of about 109.7 megahertz. And I set the span so I could see the shape of the noise that comes out. that noise that comes out should be shaped by the transfer function or the frequency response of the Q-enhanced LNA filtering. And in fact, here it is. It's about 200 kilohertz wide, which is what we expect. The span, this says 2 megahertz, so the span is 2 megahertz, so each division here is 200 kilohertz. The resolution bandwidth that I'm using is 100 kilohertz. It needs to be less than what you're measuring for the bandwidth of the noise, so that's less. This may have a little of impact, but not enough for me to worry about. So how do we get the noise figure? Well, it's over here on the right-hand side. First of all, we terminate the input of the Q-enhanced LNA in 50 ohms. So we don't have any noise coming in other than thermal. That thermal noise should be minus 174 dBm per hertz is the way they talk about it. So minus 174 dBm, our bandwidth is 100 kilohertz, so we have to add 10 log of 100,000. And then we have to add our gain because we're going through the amplifier. So we get minus 174 plus 50, that's 10 log of 100K, and the 22.1 that we previously measured for our gain. And that works out to be minus 101.9 dBm. This is what we should have coming out. What do we have coming out? Well, up here in the circled, it says minus 96.6. So I wrote that down as our measured output noise. So what's the noise figure? Well, it's simply the actual output noise minus the expected output noise. And that works out to be 5.3 dB. Again, plus or minus a dB or two because of our attenuator. And it also depends on how good the spectrum analyzer is at getting you close to the actual power that it's spitting out, minus 96.6. I have previously qualified this Tiny SA Ultra to be within about a dB or two. So our noise figure is about 5 dB. Could be off a little, but I don't really care for the reasons we've been talking about. What's arguably more important, based on everything we've been saying, is the compression point and the intermods. Remember, compression point and intermods are linked. If you find the compression point, the third order intercept is generally about 10 dB higher. 5 to 15, 10 is a good average. So this directly impacts the intermodulation performance, and we want a good 1 dB input compression point. So how do we find that? Well, let's take a look at the pictures. First of all, we had to set the thing to the right frequency and bandwidth. So we got that all done. The step attenuator is then used to find the 1 dB compression point. So here I've got these steps, and some of them are 1 dB, some are 2, some are 4. I could punch in and out the 4 dB, for example, and I would expect to see a change in level on the spectrum analyzer of 4 dB. If I only see 3 dB, then it's probably compressed if I'm actually going up in amplitude. And so that's what we do. And we ran the tests at 99.2 megahertz and then at 101.2, which is 2 megahertz higher. Doesn't have to be 2, just, whatever you're interested in. So let's see what that looks like. Here's the spectrum analyzer. We're tuned to 99.2 megahertz, which is right here. It says F0. How do I know that? Well, I had the signal turned off and I could see it, and I can see the noise peaking up there. What's this other stuff? Well, these are FM radio stations being picked up by the inductors, so they're kind of a little bit of a problem, but it's all right. Because what I'm interested in is what's happening over here, 2 megahertz higher than F0. So what I found was that with a minus 10 dBm signal at that frequency, 2 megahertz above, 101.2 megahertz, the output was minus 17 dBm. You can see up here. What do I expect it to be? Well, I expect the gain to be depressed by 26 dB relative to what the gain is at the center frequency. Why 26 dB? Well, it goes back to filter theory that we talked about in Radio Design 101. And with this type of filter, which is a so-called one-pole bandpass filter with a 200 kilohertz wide bandwidth, the half width is 100 kilohertz. So 100 kilohertz above 99.2 megahertz, I would expect to be how much? 3 dB down, right? At 10 times that much, i.e. 1 megahertz above F0, I would expect to be 20 dB down. But here we're 2 megahertz above, so that's another 6 dB. So instead of minus 20, it's minus 26. All right. So we expect the output to be minus 10 dBm plus 20 dB, that's our gain, minus 26, that's our filter roll-off, or minus 16. We got minus 17. Now, you got to be careful about that because there's accuracy issues here. What you really do is what we did over here, where we put in and out step attenuation values and made sure that we were entering compression and found the 1 dB compression point. Okay, so that's how we measure the compression points. And more importantly, minus 10 dBm is pretty darn good. That means our third order intercept intermodulation point would be about plus 5 dBm. And that's at the input. So at the output, it'd be like plus 25 dBm. And that's all running on, what do we say, 11 milliamps? So that's pretty good for a filter which is only drawing about 50 milliwatts. If we compare it to a commercial low noise amplifier, such as the one that's used inside the Tiny SA spectrum analyzer, it is in fact very good. So we're beating these commercial chips. And in fact, as I'm going to show you, we will beat the performance of an automobile radio, one of the best automobile radios I've tested. Okay, that's what we've got for lab testing and for spec sheet numbers. They all look pretty good, but let's see what's really going on in the real world. Does this hold up? First, in the indoor environment. Remember, the signals have a lot of noise in the background, but there is a station right here at 88.1. It's almost covered with noise, but some of that could be due to intermods happening here, composite triple beats and so forth. Let's see if we can pull this guy out. And also keep an eye on this one. This is the really strong station, and if we have too much gain in our amplifier, this thing could just go up close to 0 dBm or something. It could be really bad. So the desired station is about, let's see, minus 85 dBm, and this guy is about minus 30. It says minus 32, but due to the resolution bandwidth here and the signal moving around, it's probably about minus 30. So minus 85 and minus 30. So here's what we get with the filter centered at 88.1, that minus 85 dBm signal, and the bandwidth adjusted to 200 kilohertz. The minus 85, which is both signal and noise, has gone out to about minus 65, so about 20 dB of gain. This is what we expect. Meanwhile, the minus 30 dBm signal is now down close to minus 50, minus 48, something like that. So the strong signal has not only been not amplified, it's actually been attenuated from what it was before, whereas this one is amplified by 20 dB. This is exactly what we want, because we don't want these strong signals to go downstream in the receiver and hit the mixer and other stuff and cause intermods. That could happen here at the mixer if we didn't take actions in the LNA/filtering to prevent it. So the LNA with Q enhancement is doing a wonderful job, and we also have now a high intercept point mixer that is just not going to cause us any problems. So this is really awesome. This is what we want. Let's look over here at the right-hand side. We're actually down to minus 120 dBm here. Why is that? Well, that's because the filter has no gain there, and so we're just seeing pretty much the noise floor of the Tiny SA with the LNA on. This is exactly what we would predict for a 100 kilohertz resolution bandwidth. But now let's look at what the mixer would be seeing as we tune through the band. So here's what we just saw. This is what's going into the mixer. And there aren't that many strong signals that could cause intermods, and this guy has been elevated so much that even if there are intermods, it's not going to hurt us. Let's tune around a little bit more. This was at 88.1 megahertz. Here I've tuned up to 89.5 megahertz, That's where the marker is. And you can see that signal really pop up. Where was it before? Well, it was this guy right here. So now that one's being accentuated or amplified, and the one at 88.1 is now down here. In any case, this one has still, the big guy has still not popped up very much. It's exactly what we want. And I'm just going to sample a couple more of these. Here's a whole bunch of them. One problem is that if we tune close to the strong guy, then the filter doesn't roll off fast enough, but it is doing a pretty good job. So let's compare these two. So there is a signal here that we can't even see that has now been brought up to a level that's acceptable. The strong guy is over the top, but the top is only minus 30 dBm, so we might still be okay on that. So even though we're only a few hundred kilohertz or megahertz off of this center, we're able to pull this weak signal that's in the noise floor here out. All right, now let's move outside. And again, to be outside, I had to put all the stuff in my car and compare. So I'm just going to play a little video here. And what we're going to be listening to is 94.1 megahertz, which is a very weak signal in this park, surrounded by all these strong signals. And the car radio is able to pull it out, but so is ours. So here is 94.1 from our new radio, with the Q enhanced filter front end. And it sounds kind of scratchy because it's a very weak station, but let's see what this one sounds like. Pretty much the same thing. Pretty much the same thing, only actually worse than our radio. Nice. And lastly, here we are outside again, but we're now at top of the world where all of the signals are bigger, and the one that's on this tower, which is 96.3 FM, is huge. Okay, we are at the top of the world. There's that big antenna over there at 96.3 pumping a huge signal at us. And we've got our Q enhanced filter here. I set up a little bit of attenuation on the front end, not too much, and dialed in some Q enhancement, and we're picking up 88.1, but it's coming from here, our radio, out of these speakers. Let me turn up the car radio so you can hear what it does up here. So that's absolutely terrible. But that's our radio, and it's working great up here. All right, so I've kind of optimized it, and we've got some attenuation in. So I'm going to take the attenuation out. Let's hear what happens. Okay, so that's that big, huge station interfering with us. But if I just dial in a little bit of attenuation, it's totally clear. And to be very clear, the car radio is not. I'm turning its volume up. So, same station, but you couldn't listen to it. This one is perfect on our radio using the Q enhanced filter front end. Okay, so there's another pot here. This is the Q enhancement pot. So let me vary it. I'll turn it up a little bit. So it went into oscillation, so that's why it went blank. If I turn it back, so now we've got good Q enhancement. I'm going to turn it all the way back so we don't have any Q enhancement. So there, we're kind of a little buzzy now. So the Q enhancement is working well to get the station clear. So yeah, this is actually working, and you can probably tell I was excited, especially when I did that last measurement up there, and all the theory came together. So conclusions and future directions, one slide on each. Conclusions are, The new Radio Design 401 receiver with the Q Enhanced low noise amplifier meets or exceeds the performance of the best commercial receivers in automobiles. Now, I can't say that this Honda radio is the best, but of the car radios I've tested, it is definitely the best. The reason for this is the narrowband preselect filtering allows us to operate in the harsh environments, as we've seen with these spectrums that I just showed, at 1/10 the power consumption. So these field tests, the reason I was excited is because these field tests in real-world environments are validating the white paper theory from episode 1. I am very happy. But as with any research or development project, there are always things you can do better. So we often talk about future directions at the end of writing something up. It is true that our receiver is approaching the realization of an ideal receiver. And I'll call your attention to this block diagram and our discussion of that. But it still requires an attenuator for very strong signals, as we saw in that last video, due to the fact that it's only a single pole response and it has somewhat limited preselect filter off-channel attenuation. What does that mean? Well, let me take a look at these graphs on the right. The red curve is the gain to the output, so to here. The blue curve is the gain to the input of this transistor. And you can see that with the attenuator set to 0 ohms, i.e. no attenuation, we only have about 12 or 13 dB of attenuation. That's why this thing is only a factor of 10 better in power consumption. If we dial in attenuation, if we set this potentiometer to 500 ohms instead of 0, then these are the responses we get. The blue curve is down at -30, so we got 30 dB of attenuation from the input signal to the transistor. And that's going to protect this from very strong signals. So that's really good. The negative is that A, that's going to increase the noise figure in this amplifier, and B, the gain to the output of the amplifier is now only 0 dB. And remember, after that, there's a passive mixer and some filters, and so they have 15 dB of loss. So we really needed 20 dB of gain to prevent those things from affecting the receiver noise figure. So this is not great, but it's actually better than the car radio. I did some measurements on the car radio at home and then up here, and I found out that the sensitivity of the car radio, whose antenna is right here in the back, the sensitivity of it dropped by about 15 dB. It switches in attenuators to deal with this. And that's why when we looked at this video, it sounded so terrible at 88.1 megahertz. It was partially because of intermods, but also partially because it had destroyed its sensitivity. So the final future direction that I have is it would be nice if we could have additional filtering before the amplifier that didn't hurt the sensitivity of the receiver. If we could do a better filter out here in front, then we could approach this design. And we could do that, but the trouble is the automatic tuning that is required in one of these designs would get more complicated. But that doesn't mean it's not doable. So there's additional work that could be done here. And I would encourage people to think about that. Maybe there's a different topology altogether than this common base with the positive feedback. I don't know. Maybe. But this one is working. It's doing really, really well. Okay, that's the end. The end of this Radio Design 401. As always, thank you for watching. I hope this has been educational and interesting at least. And leave some comments if you have any thoughts or questions, and I'll try to get back to you. All right, thanks again for watching.